Completing the square and vertex form are very helpful when graphing polynomials, particularly trinomials. It relies on really interesting mathematics, and you might even think it's kind of neat. I think it's kind of neat how it works, but it's not used all the time, and you don't. It helps us derive the quadratic formula, which is really why we're attempting to understand it here. So, some things you need to know is that there's things called perfect square trinomials, and it's when they're factored. When these particular trinomials are factored, we get binomials that are perfectly squared. So they're very special cases, but we're always able to find a perfect square trinomial if we have a trinomial, which is what completing the square is all about. So we can't complete the square here because they're already perfect squares. X squared minus 10x plus 25 converts easily into x minus 5 quantity squared, which is really x minus 5 times x minus 5. But it's just written in a clean, neat way. So instead of writing it twice, it's like, oh, okay, we got two of these things multiplied together. We've got x minus 5 times x minus 5 together. And notice there's a whole bunch of different varieties of what we call perfect squared trinomials. So the perfect squared trinomials are a few things that you need to know, and another thing called adding zero. So if I'm taking a number a and I want to get a out when I'm done doing some things to it, I can always add. I'm going to call it adding zero, and I can add a number so long as I take it away again. And notice that 10 minus 10, they cancel each other out, so I get a when I come out. So if I were to do those two things, the plus 10 and then the minus 10, that's kind of like I'm adding this funky form of zero. And it's going to be very helpful for us as we work to complete the square. So those are the two big things that you really need to understand in order to understand completing the square. So if I were to visualize completing the square, I want to show you what that looks like. So if I have x squared, I've got the x square. Notice it's a square and each side length is x. And I've got 12 x's. X, 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 x. There's 6 of them, 7, 8, 9, 10, 11, and 12. And these have side length x by side length 1. And then I've got 36. Each one of these green squares represents a number 1, and we have 36 of them because that's what fits in here. And notice that this makes a perfect square. And each square has side length 1, 2, 3, 4, 5, 6 here, and then side length of x there, so the total length is x plus 6, and it's a square, so it has the same length on each side, and so we get x plus 6 quantity squared, and that makes this visual representation. Well, this specific situation is very, very special because we don't always get a square, and so I'm going to move on to the next slide where we're not going to have a perfect square. In fact, we're going to have mostly a perfect square. So again, we have got that x squared, the x squared space there, and we've got the 12 x's. And instead of having the 36, which make the perfect square, we only have 25 of these green squares. So currently, we only have 25. So how many more squares do we need to complete this square? So we think, how many more squares visually do I need to complete this square? Well, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I need 11 more squares to complete this square. So mathematically, how do we work to complete this square? So we start with what we originally had, plus 12x plus 25. And in order to make it a perfect square, I'm going to need to add 11 because that's what would make it a perfect square. But I can't change the original problem, so I have to add 0. So I have to add 11 and then take 11 back away. So in completing the square, now I'm going to combine like terms of the things I already have. So I've got x squared plus 12x, and 25 plus 11 is 36. And then that 11, it's just an extra 11 that's going to hang around for the rest of this problem, but hopefully this is going to make sense. Well, notice if you look back, if you rewind for just a minute and a half, you'll see, oh, this is the perfect square that we had before. And what are the side lengths of this square? Well, it's x plus 6, and then again x plus 6. But that's assuming that we have all 36 squares. So I can condense this to x plus 6 squared minus 11. So this process of adding and subtracting the proper amount of green squares is called completing the square. And if we think about it as a equation, this actually, if we were to graph this, this is a quadratic, and the vertex of this quadratic is at -6, -11. And if you pull out a graphing calculator or go to Desmos and graph this equation that's circled down there in black, and you look at it, you'll notice that the vertex, the minimum point of this quadratic is at -6, -11. So I can't just leave you there. We're going to do one more, and just to see how it goes. So currently we've got, it looks like we've got x squared plus 8x plus 10. How many more squares do we need to complete this square? Well, we need 1, 2, 3, 4, 5, 6 more squares to complete this. So if I'm going to add, I'm going to eventually add 6 and subtract 6. So x squared plus 8x plus 10. I've got to add 6 and subtract 6. And when I look, how big is this side? Well, it's an x squared, so I've got x plus 1, 2, 3, 4. So x plus 4, and then again x, and then 1, 2, 3, 4. But that's assuming x plus 4. That's assuming we have all of those pieces. So those pieces make x squared plus 8x plus 16 minus 6. That becomes x plus 4 squared, because I have a square where each side is x plus 4 minus 6. And if we were to graph this, the neat thing is that my vertex of this graph would be at -4, because -4 makes the inside of that quadratic 0. -4, -6. I think that's really neat. And maybe I'm just a nerd and I'm geeking out over this, but I think that to get the vertex from just simply adding and subtracting some things is really a neat thing, and we can do this really fast. So at this point, you may be wondering, what if we don't have these tiles and these representations like that, or what if it doesn't work out quite nicely? Well, when we look through each of these, you should or could see a relationship between this number, and this number. Pause the video for just a moment to see if you can see the relationship between maybe even this number and the thing that is in our perfect square. Okay, hopefully you've taken a moment, paused the video, and looked, but do you notice that -10 and -5, half of 10 is 5, half of 14 is 7, half of 6 is -3. This is a little bit weird because we can factor out a 2. There's a common factor of 2. And so then I'd be left with x squared minus 6x plus 9. Oh, but look, if that has the common factor out, then that -6, half of -6 is -3. So hopefully, hopefully you see that relationship. There's another relationship that I want you to see, and it's I think it's kind of neat that if I take that number, -5 times -5, that's 25. 7 times 7, that's 49. -3 times -3, that's -9. And again, -3 times -3 is 9. And that is a powerful relationship that I want you to see. If we were to do that, recognizing, if we're here, we can start to make that relationship. Okay, so in my perfect square trinomial, I'm going to get x minus 3 squared is going to be my perfect square. Well, what does this have to be? Well, negative 3 times negative 3 is 9. And half of negative 18 is negative 9, so x minus 9 squared. 9 times 9 is 81. This is a little bit trickier because we've got this extra thing here that we have to consider. So if my perfect square is going to be x plus half of 10 is 5. 5 squared is 25, but we already have 5, so this has got to be 20. You can think about it like that. Let's try this last one. Our perfect square is going to be x plus half of 14 is negative 7. So really, I should have written x minus 7. X minus 7. And 7 squared is 49. So how do we get this to be 49? Well, 55 plus blank equals 49. What's that got to be? That's got to be negative 6. So in this space, negative 6. And that gets us our 49. Hopefully, take a moment to maybe peruse this section again. But I think like what completes this square isn't too challenging. So there's a way that we can always make this work. We can take this b term is always this middle term in front of the x, and we can cut it in half. So we take half of the 8 is 4, we square that, and then we can add and subtract that in our equation. And this only works, I want you to be really, really careful, this only works if the leading coefficient is 1. So if there's nothing in front of the x squared, then this will work. And I'll show you how this works because it's slightly different than what we just we're working on. So if I take the middle term, the b term, x squared plus 8x plus 10, and I add and subtract it from, I take the b term, cut it in half, and square it. 4 squared is 16, and if I add 16 and subtract 16, this is my perfect square. That now is my perfect square, and this junk is the leftover stuff. So I get my x plus 4 squared, and my leftovers are negative 6. Again, my vertex, if I were going to calculate a vertex, would be negative 4, negative 6. That's the coordinates of the vertex. So we take the middle term, cut it in half, square it, add and subtract that. Only works when the leading coefficient is 1. So here are a couple of practice problems. We're going to take the b term. The b term is 4. We cut it in half. So that's 2. And square that number. So whatever we got before we square it is 4. So I'm going to take my x squared plus 4x plus 11. I'm going to add the 4, and subtract the 4. This is my perfect square. I get x plus 2 squared, and my leftovers, 11 minus 4, and my vertex, if I were to calculate the vertex, is negative 2, 7. Last one, go ahead and try it on your own. There is a quirk to this. It's not going to be whole numbers, so be prepared to try this one without whole numbers. Go ahead and pause the video, try it on your own. The same process works for completing the square here. All right, hopefully you've taken a moment to pause the video and give this a try. I'm going to take my b term. My b term is 5. I'm going to cut it in half. Half of 5 is 2.5. I'm going to take that number and I'm going to square it. I'm going to take that number and I'm going to square it. 2.5 times 2.5 is 6.25. So when I go into my equation, x squared plus 5x plus 2, I'm leaving space, plus 6.25 minus 6.25. This is my perfect square. X plus 2.5 squared, and 2 minus 6.25 is negative 4.25. This is my completed square. The vertex of this equation is negative 2.5 and negative 4.25. I hope this video was helpful. It's kind of a neat trick, but it will help us when we start to understand the quadratic formula. So that's where we're headed with this. Thanks for watching the video. I appreciate it.